Hello everyone, and welcome back to this series on elementary probability in statistics. Today we're going to be continuing our exploration of elementary statistics and discuss some very important metrics that are commonly used. There's going to be three different groups of metrics that we're going to discuss. The first group is going to be called the measures of central tendency, the second will be the measures of position, and then the third will be the measures of dispersion and variation. So, what exactly is a measure of central tendency? So it is just a metric, which is just a number, that describes a set in terms of its central position. So one may ask, what is central position? Well, technically speaking, this phrasing is very subjective, and it's also very vague, which is why we have several different types of measures of central tendency, such as the mean, median, and mode, and a couple others that you probably have already heard of. So what I want to do is just go through some of the most common ones and discuss their differences and similarities between one another. So as a guiding example, let's suppose that we have this finite set S that contains the numbers 3, 7, 7, 18, 22, and 41. So the first measure of central tendency that I want to introduce is referred to as the midrange. The midrange is actually one of the easiest metrics that you can calculate in regards to a measure of central tendency, and it's calculated by doing half of the sum of the maximum of the data set and the minimum of the data set. So you take the smallest, the largest value, add them together, and then divide by 2. So for our particular example, that's going to be equal to 1/2. So it's already sorted. So our minimum is equal to 3, and our maximum is equal to 41. So we're going to have 41 plus 3, and that's going to be equal to what? So that's going to be half of 41 plus 3. That's going to be 44. So this is going to give us a midrange of 22. Okay. So that is what we call the midrange. The second measure of central tendency that some people will use is what is called the mode. And the mode is going to be equal to the most frequent data point. So the most frequent data point. So if we look here in our set, 3 repeats once, 7 repeats twice, 18, 22, and 41 also repeats once. So since 7 has the highest frequency in our data set, then we say that 7 is the mode of our data set. So we will just simply write that the mode is equal to 7 for our example. Let's also stay consistent with the coloring that this, for example, is equal to 7. Now, I just want to briefly mention that sometimes calculating the mode is sometimes not always the best. Take, for example, we have a frequency distribution that kind of looks like this, where this is equal to, for example, 45, and this point right here is like 82. So we clearly see that the mode of this data set is equal to 45, so mode would be equal to 45, but you might also notice that this set also has another number over here that is 82, which technically speaking is greater than or equal to most of the values around it. So if I were to partition this data set into two categories, then technically speaking this value here, mode, would be equal to 82. So pretty much what you can do is you can split your data into subcategories and say that the left mode is equal to 45 and the right mode could be equal to 82. And sometimes people will say that even though these are not equal, there's technically speaking two modes that describe the shape of this data set. And some people will refer to this as being a bimodal data set. You could also have trimodal and tetramodal data sets, which we won't get into, but pretty much the idea follows the same exact way. So the next metric that people will often use is referred to as the median of the data set, and this is the middle point of a set of ranked, some people will also use the word ordered from least to greatest, data set. So let's just actually go through an example of how to calculate the median. So keep in mind our set was equal to 3, 7, 7, 18, 22, and 41. So it's already sorted from least to greatest. And if we were to split this set in half, it would be between 7 and 18. So the middle point of a data set, if the set is even, right? So this is an even set of size, in this case 6, that's going to be our sample size, is going to be the average of the middle 2 points, right? So the median is going to be equal to 7 plus 18 divided by 2. So that's going to be equal to 25 divided by 2, which in this case is going to be equal to 17.5. So 17.5 would be the median of that set. Now let's take another example where we have another set, let's call it T, that has an odd number of points, so 5, 8, and 9, let's say. So this is an even or an odd set of size n is equal to 3. So the median for this particular case, if we were to split it in half, it would be around 8, and that actually would be defined to be the median. Right? So the median in this case would be equal to 8 for odd. So if it's an odd cardinality data set, then the median is always in that data set. And if the set is even, then the median is always equal to the average of the middle two numbers. So that's the mid-range, the mode, and the median. So let's introduce our fourth measure of central tendency. And some people refer to this as the arithmetic mean. Some people will use this phrasing to be the average, but there are different types of averages, so I highly recommend not using that terminology, but be aware that some people do. And some people will also get rid of this word arithmetic and just say the mean of the numbers, but there are also different types of means, geometric and harmonic means being the three of the most common, but usually when people say mean, they're usually talking about the arithmetic mean. So the arithmetic mean is going to be defined to be equal to the sum of your data set values, so x1, x2, all the way up to xn, all divided by the number of data points you have. And we can write this in summation notation as 1 over n times the sum from k is equal to 1 to n of xk, where xk is an element that belongs to our set S. So for our particular data set S, our values in our set were 3, 7, 7, 18, 22, and 41, and we have a total of 6 numbers. So once we actually work out that calculation, we're going to have an arithmetic mean of 16.33, right? And some people will even abbreviate this as x bar just for notation, if that is the sample mean or the mean of a sample. Right? So those are 4 of the most common measures of central tendency that people work with. Now that we have 4 measures of central tendency to work with, now let's discuss a couple things that set some measures apart from others. So now we're going to talk about sensitivity to outliers, and you're going to hear sensitivity sometimes referred to as robustness or the lack thereof. So when a metric is more sensitive, some people will say that that metric is less robust, and if it's not very sensitive, then we're going to say that that metric is more robust, right? So they're in some sense synonymous to one another. There is some subtle differences in definitions that people use in more advanced mathematics and statistics, but we'll discuss those formalities at a later time. This is just here to give you a sense of the idea of what it means for a metric to be robust. So let's take our data set 3, 7, 7, 18, 22, and 41, and let's introduce a number that is significantly different from the rest, right? So 3, 7, 7, 18, 22, 41, yes, 3 and 41 are significantly different from each other, but 1000 is significantly different from all of the rest, 3 through 41. So sometimes people will refer to this as an outlier. Now classifying data points as outliers of a data set also is another potentially difficult task, because you in some sense have to know the underlying distribution of the population to classify something as an outlier, which most of the time we don't. But it's clear to see that with respect to the sample, that 1000 value is significantly different from the rest, so that much we can see. So is there a significant difference in the metric values between S and S star, where S star is just S with an outlier introduced? So let's actually look at each of the 4 measures that we have up to this point. So we have, for example, the median. We have the arithmetic mean, which I'll just call the A mean. We have the mode, and we also have the mid-range, right? So we've already calculated these values for S, and you should also try and to calculate them for this new set S star with this number 1000 added in. So for our particular values, what did we have? So we have median, arithmetic mean, mode, and mid-range. Let's see if I can make my table a little bit more nicer to look at. Right? So here's a nice little table, right? So what was the median, mean, mode, and midrange? So those came out to 17.5, approximately 16.33, 7, and 22. And I leave it to you to calculate, just for practice, what these metrics would for S star would be. But you should find that this is going to be equal to 18. This is going to be 156.86. This is just going to be equal to 7, and this is going to be 501.5. Obviously, all has changed except for the mode. So now what I want to do is actually construct the change in these, right? So the delta, or the change in, I'll just define to be equal to the absolute value of the metric for S minus S star metrics, right? So the metric distance between them. So what's the difference between 17.5 and 18.5? That's obviously a distance of 0.5. The distance between 1633 and 156.86 are actually quite large, 140.53. The mode didn't change, and this is going to be 479.5. So between these, what can we say about the robustness of median, arithmetic mean, mode, and midrange with respect to one another, right? So which one of these changed the most? So we can clearly see that the midrange changed the most. Therefore, we will say that the midrange is not a robust representation or a robust metric of central tendency. And if we say the median, so the median changed the second least, therefore we can say that this is more robust, right? Significantly more robust than that of the midrange, and also compared to that of the arithmetic mean. Right? Now you might be thinking, what about the mode? Well, didn't mode technically change the least? The answer is yes, but the mode typically does not necessarily represent the middle. So if you think about what the mode actually represents, it just focuses on the frequency, not necessarily the locations of the data set. So for example, if our data set looked kind of like this, actually let's focus on, let's do a little bump there, pretty much flat, and then let it steep off here. If you were to say where's the middle of this box, most people would locate somewhere around here. So pretty much what we're trying to do is find a measure of central tendency that represents that little x in the middle. But you can clearly see in this picture the mode would be located over here, which obviously is significantly different from that particular quote-unquote middle value that most people in society would agree upon, right? So usually when we talk about robustness, we usually do not consider the mode, and we usually consider the median, the arithmetic mean, the midrange, and maybe a couple other metrics. Right? So that's what we mean when we say is a metric sensitive to outliers, or equivalently, is a metric not robust, or is it robust with respect to outliers. Another metric, or similar metric that I want to discuss is another thing, right? So also a little bit of notational difference. So we have x bar, which we know to be 1 over n times the sum from k is equal to little n of xk. And this notation, in case you don't remember, is obviously going to be a statistic, right? Why is it a statistic? Because it's for a sample, right? In particular, it's for sample S. So if we were to draw a picture, right? So here's our population P, and then here's our sample S, right? So our x bar is representing the average of this particular set. So we're trying to estimate the center of the population P, right? So we can say, from our perspectives of statistics, parameters, samples, and populations, so if the arithmetic mean is for S, we can use it to estimate the value of mu, right, which is the arithmetic mean for our population P. So is there any difference between the calculation for arithmetic mean and population mean, mu? Technically speaking, there is, because mu would be equal to 1 over capital N times the sum from k is equal to 1 to capital N of xk, right? So technically speaking, this would be a parameter, right? And this is for a population. Right? So there's a subtle difference. It might not look the same on the surface, but technically speaking, this calculation for this parameter contains usually, most of the time, more values than the calculation of a statistic is. Right? So again, this mu is a parameter, x bar is a statistic, and there we say that x bar is an approximation. Some people also say, or a point estimate. Point estimate for mu, right? Because usually what we're trying to aim to do is to estimate that population parameter mu and estimate it with some statistic, in this particular case, x bar. Now, could you estimate mu with the median? Definitely yes, but x bar is sometimes viewed as a quote-unquote ideal or unbiased estimator for mu. But we'll get into what it means for an estimate to be unbiased a little bit later. Another thing I also want to mention with respect to sample means, since they're so commonly used, is in regards to partitioning. And we already know that partitioning does have some advantages from the sampling perspective. So let's assume that S is partitioned into, let's say, S1, S2, and S3. And what do we mean by partition? Well, S1 union S2 union S3 equals S, and S1 union S1, S2, and S3 are mutually exclusive, i.e. they do not have any overlap. So what is the average? And when I use average, I'm talking about the arithmetic mean here of the values in S. Right? Now, let's draw a little picture to sort of talk about, what exactly we're doing here. So we have our sample S, and then we're partitioning this into 3 regions, S1, S2, and S3. So the values in S1 are going to have an average, let's call it x bar 1. The average of the values in S2 are going to have an average, let's call it x bar 2. And the values in S3 are going to have an average, let's call that average x bar 3. So here's a true-false question for you to think about. So true or false is the average for the entire sample, which I'm going to refer to as x bar bar, and some people will call this the grand mean. Is this equal to x bar 1 plus x bar 2 plus x bar 3 all divided by 3? So is that true? The answer, take a guess, usually no. So that's unfortunate, right? So the grand mean is not the average of the averages in most cases. What the grand mean actually is, x bar bar will be equal to n1 times x bar 1 plus n2 times x bar 2 plus n3 times x bar 3 all over n1 plus n2 plus n3. So this is what the grand mean is equal to. And you can technically view this as a weighted average of sample means. And I'll leave you theoretical people to prove that this is actually the formula for the grand mean. So let's just do a quick calculation example just to make sure you understand. So suppose that A and B partition some sample S where A has the summary statistics n is equal to size 52, and x bar A will be equal to 14. And B has the summary statistics, n is equal to 175, and x bar B will be equal to 82. Right? So if I were to pull all of these values together from A and B and consider the average of S, what would that average be? So the average, or the grand mean of all of these values, which technically speaking is the average of set S, because keep in mind, what is S? Well, S is just the pooled distribution of A and B. So if I were to delete this line in the middle, what would be the average of all the values in A and B together, right? So the 52 A's and the 175 B's. So from our conclusion above, we have that that's going to be equal to 52 times 14 plus 175 times 82 all over the sum of the sample sizes, 52 plus 175, and you're going to find that that's approximately equal to 66.42. So if you were to pull all those values into one sample, the average of all of them would be approximately 66.4. Now let's move on to the second class of metrics that are commonly used in statistics, called the measures of position, which are metrics that describe a point, element, or individual with respect to another point or set. And we've actually already discussed to some degree 3 common measures of position: the minimum, the maximum, and the median. So in this particular horizontal chart, I have the minimum, maximum, and median all drawn. So what exactly do they mean with respect to the measure of position? So keep in mind the data set S, so 100% of S is greater than or equal to the minimum. And we also have that 100% of S is less than or equal to the maximum. And for the median, we have that 50% of S is greater than or equal to the median, and also 50% of S is less than or equal to the median as well. So it goes both left and also right. From this particular picture, we can actually introduce very easily other measures of position, which are known as inner quartiles. And the word quartile pretty much infers what we're going to do. So what we're going to do is we're going to break this data set S into quarters instead of halves. So we're going to say that, for example, right here is the first inner quartile. And then over here, what we're going to have is Q3. So you might say, okay, that's Q2. That means this is Q0, and this is Q4. So Q0, 1, 2, 3, 4 breaks our data set S into quarters. So what do we have with respect to Q1? Well, 25% of S is greater than or equal to R, or less than or equal to Q1. And 75% of S is greater than or equal to Q1. And similarly speaking, for Q3, we have 25% of S is greater than or equal to Q3, and 75% of S is less than or equal to Q3 as well. Right? So we've broken our quartiles into, it separates things in terms of 25 percentiles. So how do we actually find Q1 and Q3? So we define this as the medians, because it separates it into 50 percentiles of the left and the right, of SL, the left-hand portion of S, and SR, the right portion of S, where SL union SR is equal to S, and SL is less than SR. That is, for any value in SL, it is less than any value in SR. So let's go through a computational example of how we would find those interquartiles Q1 and Q3, since we already know how to find Q0 and Q4, and also Q2, aka the median. So let's bring back our data set S, which was, 3, 7, 7, 18, 22, and 41. And let's actually draw a little picture that describes these quartiles. So what you're going to see is 3, and then some other points scattered here, and then 41, and then our median, which was that 17.5. And what we're going to do is we're going to draw a box around these 2 points, and what we're going to do is we're going to shade and that, and that, and then we're going to draw some little tails on this box. So sometimes people will refer to this as a box plot. Some people also call this a box and whisker plot for the data set. So our goal is to find Q1 and Q3 that represents the inner quartiles, or the boundaries of that inner box, because 50% of the data should be between Q1 and Q3. So 50% of the data should be located here. right? So what do we have in terms of Q0? So Q0 obviously is going to be equal to 3. Q4 is obviously going to be equal to 41. And Q2 we found already, again, to be equal to 17.5. And there are some different ways to partition this, but nonetheless, there's for this particular data set, there's only one trivial way to partition it, 3 on the left and 3 on the right of our median. So what we're going to do is we're going to define SL to be equal to 3, 7, and 7, and we're going to define SR to be equal to 18, 22, and 41. And then what we're going to do is we're going to find the median of this set, the median of this set, and define them to be Q1 and Q3. So Q1 will be equal to the median of this set, so that's going to be equal to this 7, and Q3 will be equal to the median of this set. In this case, that's going to be equal to 22. So once we have Q1 and Q3, then we have our what we call inner quartiles. Now I do want to make one very subtle note. Some people will exclude Q0 and Q4, and sometimes Q2 from SL and SR, right? And then you get some variations on inner quartiles, such as inclusive inner quartiles and exclusive inner quartiles. Because if we have our data set, right, so if we have S is equal to 3, 7, 7, 18, 22, and 41, and we exclude the tail points, so 3 and 41 are definitely out, and then we consider the inner quartiles of the left and right. So here we're going to have Q1 is equal to 7 still, but Q3 will be equal to the average of 18 and 22. That's going to be equal to 20. And as we clearly see, that gives us different answers. But usually if your data set is well representative of the population and you have a lot of data points, roughly our inner quartiles, our outer quartiles should be roughly the same, although they will have their subtle differences between them. Right? So that gives you two different types of measures of position. We have our minimum, maximum, median, and also our inner quartile. So technically you could cluster all 5 of those together and just call them quartiles. The next one kind of tries to generalize quartiles and just goes to percentiles. And I'm going to go for the convention that these are lower percentiles. So what is a lower percentile? That means some percent, so P% is less than or equal to this point. Right, so we're trying to find this point giving some value of P. So if I say 30% of people are less than or equal to this point, who is this point going to be equal to? And then it's up to you to find this point. So what we're going to do is, let's suppose that we have the size of this data set is equal to n. So we ask n people what their favorite or how many cats they like to have in their house or something like that, and then n is going to be the number of responses. So what we're going to do is we're going to define the lower pth percentile, which I will denote by x superscript L for lower, and then p% on the bottom, and this is going to be equal to a particular value xk in our data set S. The only thing is you have to know what k is. So k is going to be equal to p divided by 100 multiplied by n, and once you get that number, you're going to round up, right? So that's what this little half brackets is. So this just means round up, right? Some people will use round down also, but most of the time round up is more efficient. So let's actually look at an example to sort of see how to calculate percentiles for discrete data sets. So let's assume that we have some data set A, which is going to have the numbers 8, 12, 14, 15, 17, 82, and 101. So how many values are in this data set? You see 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 7. So n would be equal to 7 in this case. And they're also ranked, ordered from least to greatest. So this is going to be x1, x2, x3, x4, x5, x6, and x7. Notice the last point is always x subscript n. So let's assume that you want the percentile associated to 30%, and let's assume we're going for lower percentiles here. Then using this formula, the index for the 30th percentile is going to be equal to the ceiling, or the rounded up version, of 30 divided by 100 times 7. So when you do 30 over 100 times 7, you're going to get 2.1, and then 2.1 rounded up is going to be equal to 3. That means the 30th percentile will be equal to x3. So the 30th percentile, the lower 30th percentile, will be equal to x3, and x3 in this case is 14. So that means 14% of the data, 30% of the data is going to be less than or equal to 14. So that's another measure of position that a lot of people will use in practice. Another measure of position is what we refer to as the mean-based difference score. Mean-based difference score. Mean-based difference score. And we're going to note that this is dx is equal to x minus x bar. So pretty much what does this tell you? Well, this just describes how far, or not necessarily how far, but where are you with respect to x bar. Some people will use the arithmetic mean for x bar. And notice I put mean based in this parentheses because some people will ask the question, where are you with respect to the median? So that would be a median based difference score. And the only difference is, instead of using the mean here, you would just use the median. So if, for example, our mean is going to be equal to 16.33, and I ask you what's the difference score associated to 18, that would just be equal to 18 minus 16.33, and that's going to be equal to 1.67. So that's the difference score for 18. One important observation, and this is going to be very important later, is that if 1, the difference score, is positive, then that means x is to the right of x bar. And if the difference score is negative, what does this mean? So that's x is to the left of x bar. And lastly, if the difference score is equal to 0, that means x is precisely equal to, or is, x bar. Right? So those are some observations that you can immediately get from the difference score. Now there is another type of score, which is called a z-score, but we'll talk about that in just a moment. The third class of metrics that we're talking about today is known as the class of measures of variation. Some people also call them the measures of dispersion. So what are these? So what these metrics describe is how spread out the values of a data set are with respect to one another. So let's start with the first one. So the first measure of dispersion that we're going to discuss is referred to as the range. So the range is going to be defined to be equal to the maximum value of the data set minus the minimum value of the data set. And from the perspective of quartiles, you should know that this is just going to be Q4 minus Q0. And another variation of the range is referred to as the inner quartile range. Some people will just use IQR to represent this. And this is just going to be equal to Q3 minus Q1. So it's the difference of inner quartiles versus the range, which was the difference between outer quartiles. So it's very easy to see that the outliers are usually going to be on the left tail or the right tail most of the time. So this range is obviously not robust at all compared to the inner quartile range, which will be more robust compared to that of the range. Right, and that's just because outliers are usually on the tails. Another measure of variation that some people will use is abbreviated by SAD, which is in short for the sum of absolute differences, aka SAD. And this is going to be equal to the sum from k is equal to 1 to n of the absolute value of xk minus x bar. So you can also say that this is the mean, or the arithmetic mean based. sum of absolute differences because technically speaking we can change that x bar to, for example, the median if we want a more robust measure of variation. So let's actually look at an example of how we would calculate the sum of absolute differences for a set. So let's assume that our data set S is, let's choose a short data set. Let's do 5, 8, 12, and 13. And I leave for you to verify that the arithmetic mean of this data set will be equal to, what is that, 9.5. So once we have the arithmetic mean, then we can calculate the mean-based sum of absolute differences. So what would that be? So the sum of absolute difference will be equal to, so we're going to take each of the values, 5, and subtract the mean, take the absolute value, and then take the next value, 8 minus the mean, and then the next value, take the value, subtract the mean, take the absolute value, then the next value, 13, subtract the mean, absolute value, and add. And once you do all that, you're going to get a sum of absolute difference of 12. So obviously, if your sum of absolute difference is close to 0, that means everybody is similar to one another and close to the mean, and the sum of absolute difference is large. That means it covers a wider range of values. And it's actually important to even note that if the sum of absolute difference is precisely equal to 0, then this is true if and only if all x's are equal to one another, right? And sometimes people will say that this means there's no variance in the data set, right? So that's the sum of absolute differences. A very similar metric to the sum of absolute differences is referred to as the sum of squared differences, sometimes abbreviated by SSD. So take a guess of what the sum of absolute differences is going to be. This is going to be equal to the sum of squared differences, xk minus x bar, the quantity squared. And obviously, yes, this is going to be a mean-based sum of squared differences because, yes, again, you can replace the mean with the median if you want a potentially more robust measure of variation. Right? So it's pretty much going to be the same exact thing. So instead of doing 5 minus 9.5 and then absolute value, you're just going to do 5 minus 9.5 and then square that. And then 8 minus 9.5 and then square that. And then 12 minus 9.5 and then square that. 13 minus 9.5 and square that. And then you're going to get some number. So for our particular example, I'll leave it to you to verify just for some practice that this is going to be equal to 41. It's also very important to note that x minus x, if both of them are in inches, then when you do that unit, you're definitely going to get a squared unit on that sum of square differences. So it's going to be a little bit more harder to interpret how large is large and how small is small for the sum of square differences. A variation on the sum of square differences is referred to as the mean base variance. And there's actually two variations for variance. One is for the population P and the other is for samples S. So the population variance is going to be represented by sigma squared and will be equal to the sum of squared differences divided by the population size, capital M. And for samples, it's going to be abbreviated by little s squared, and that will be equal to the sum of squared differences of the sample divided by little n sample size minus 1. Since we're working with sample, most of the time this is usually the one that you're going to be working with. So if we continue the example from the sum of squared differences, that's going to be equal to 41 divided by your particular sample size. We had a sample size of 4, so that's going to be 4 minus 1. So that's going to come out to approximately 13.67. And keep in mind, dividing by a scalar will not change the unit, so this is still going to be in units squared. Right? So since it's in units squared, it's again hard to interpret. So maybe if we take the square root of this metric, we're going to get more easy to understand metric. And that's where the next one is going to come into the picture. So here we're going to have the standard deviation of the data set, and yes, we're going to have two variations. The first is going to be for populations, and the second is going to be for samples, mainly for notation for this one. So sigma will be equal to the square root of sigma squared, so standard deviation is the square root of variance, and similar little s will be equal to the square root of little s squared. So since we're working with a sample, this is going to be the one that we're going to be working with. So this is going to be equal to approximately the square root of 13.67. And once you take the square root of that, you're going to get approximately 3.6968. And that's going to be in the original units that we had before. The next measure of variation, so notice that we have lots of measures of variation, so because they vary so much, I guess. And this is called the coefficient of variation. Well, imagine that. So what is the coefficient of variation? We're going to have three variations for this. The first is going to be for populations, and the second is going to be for samples. So for populations, this is going to be equal to, some people will use CV for this. This is going to be equal to sigma divided by mu, and for coefficient of variation for sample, this is going to be equal to S divided by X bar. So it's always going to be standard deviation divided by means. For our example, since we're working with standard deviation, this is going to be the one that we're going to be working with. And if you use all the data that we've collected so far, this is going to come out to approximately 3.891. And what is the unit? Well, standard deviation is in units, and X bar is in the same exact units, but when we divide, it cancels the units. Therefore, this does not have any unit at all. So if you want to compare, for example, the variance in heights versus the variance in weights, those are completely different units, so you can't really compare them directly to one another, but you can find the coefficient of variation for heights and weights and then compare them, because now they don't have the same exact unit, and then hence are a little bit more comparable than they were before. Now I need to give one important note about the coefficient of variation. Some people will multiply coefficient of variation by 100. But keep in mind, this is not necessary, because it's very, very possible that the coefficient of variation is extremely positive, and it's also possible that this is extremely negative too, because keep in mind, X bar can literally be 0, it can be negative, it can be positive, and standard deviation can be very large or very small. So the coefficient of variation is not between 0 and 1, so multiplying by 100 is just a convention for whatever purpose. I guess some people will make a meaning out of it, but mathematically it is not a necessary thing. Right? So here we have several different measures of variation: range, interquartile range, some is absolute differences, some is square differences, variance, standard deviation, and coefficient of variation. All have their pros and cons with respect to each other, units being one of the differences, and robustness being another that you could, of course, analyze on your own. Right? So obviously lots of different metrics here. So what I want to do now is kind of summarize these measures of central tendency, position, and variation all into one short little table, just to make sure everything is organized on your end. So what are all the metrics that we've discussed so far today? So the very first class that we discussed was the metrics of central tendency. So the metrics of central tendency. And what were they? So let's see if we can list them. So first we had the midrange. The second we had the mode. The third we had the median. And then the fourth we had the arithmetic mean. So what can we say about the robustness for each of these four categories? So for mid-range, was that robust? Obviously not, so that's not robust, so I'm just going to write NR. Was the mode robust? Yes, but it wasn't really representative of the middle. Was the median robust? Yes, it's a lot more robust than the mid-ranges. And is the arithmetic mean robust? Not really, so we're just going to represent that as NR. Also, in terms of the units, so this, let's actually create a little column headers, right? So this will be our metric, and this is our robust question, and then the units on each of these. So if we are measuring lengths of turtles in inches, then mid-range, mode, median, and arithmetic mean will all be in the original unit that your measurements were in, right? So that's always a good thing. One of the other classes that we discussed was the measures of variation and dispersion, measures of variation and dispersion, and we had quite a few measures to discuss here. All right, so let's see if we can list them all. So first we have the range. Second we had the interquartile range. The third, we had the sum of absolute differences. We also had the sum of squared differences. We also had the variance. We had also the standard deviation. And we also had the coefficient of variation as well. So we had quite a few different metrics there. All right, so let's create our little summary table. Same criteria, robust or not, or kind of robust, kind of not robust, and the unit associated to it. So for range, that's definitely not robust because it depends on the maximum and the minimum. IQR, a little bit more robust than that. Sum of absolute difference, not robust, not robust, not robust, not robust, and also not robust as well. And why are those all not robust? Because they're usually based on the arithmetic mean, which is not robust. And also, what about the units? Well, range is in the original units, IQR the original units, sum of absolute differences in the original units, but sum of square differences in square units. Same thing with variance. Standard deviation fixes that, and the unit for the coefficient of variation is none. Right? And also, let's bring back a little note that we had. So note, sum will replace x bar with the median to help with robustness. Right, and that's a good thing. And this would be applied to sum of absolute differences through coefficient of variation. Right? So replace x bar with median, and sometimes that can increase the robustness of your measures of variation in this dispersion. And the third class that we discussed for metrics is the metrics of position, and we had a couple of these as well. So the first one was quantiles, or quartiles, which we abbreviated by QK. So that includes your minimum, maximum, medium, and interquartiles Q1 and Q3. We also discussed how to calculate percentiles, or one way to calculate percentiles for discrete data sets. And we also discussed difference scores. We usually do not talk about robustness in terms of position, but technically speaking, you could. But I'm only going to be mentioning the units for each of these. So the unit for quartiles will be the original unit. The unit for percentiles will also be the original unit, and difference scores will also be the original unit. And I leave to you to figure out what those are, right? And same thing applies if you want to make our difference score more quote-unquote robust, replace the mean with the median. But usually, again, robustness is not discussed for percentiles. But there's also another measure of position that we didn't discuss, and that's usually referred to as z-scores, which will not have any unit at all. So let's actually discuss, just briefly to close, this measure of position. So the z-score for x will be equal to the difference score divided by the standard deviation. So obviously this is a sample definition. So if we sort of expand that, that's going to be x minus x bar, all divided by the standard deviation of s. So you can clearly see that x and x bar are going to have the same unit as s, so unit divided by unit gives you no unit. So that's why z-scores do not have any unit at all. So if we sort of go back to our 4-element example, which was 5, 8, 12, and 13, again, I leave to you to calculate that the mean for this was 9.5, and the standard deviation for the set was approximately 3.7. So if I ask you, what is the z-score for element 8, that's going to be equal to 8 minus the mean all over the standard deviation 3.7, and that's going to be approximately equal to negative 0.4058. And some people will say this means that approximately 8 is negative 0.4058 standard deviations to the left of the mean. But we'll talk about, intervals and distances with respect to means and medians and distributions of frequencies a lot later in the series, but don't worry, we will get there eventually. But this is just a crash course of some of the most common measures of central tendency, variation, and position that people use in the realm of statistics. Now, are there a lot more different metrics that people use? Of course, but these are the fundamental ones. So I hope to see you in the future videos, and I hope you enjoyed this one. Take care.